But I want to show you one more thing on Cramers Rule, and then you guys won't be here until your test on Thursday, right? But we are reviewing tomorrow, and technically on Wednesday. Am I off on that, or am I right? Yes. So today is the last day of new material. When I'm done covering Cramers Rule, which I don't think that you're going to dislike, it's not necessarily the most wonderful way to solve a system, but it is a way, and it is in your course of study, so we talk about it. But we're going to talk about it, and then if we want to revisit some of those weird rules, we can go revisit those rules. All right? We good? Okay, so let's check out Cramers Rule. All right, so if you look at Cramers Rule, I want to say, gosh, I don't know, 50-something? 57?
73.
73? Good night, I've added that much. On my right here it says 57. Yeah, I've added a lot of junk in here over the last couple of years. Okay, so 73, Cramers Rule. Let's take a look. So I'm going to start out showing you Cramers Rule with just basic X and Y variables, okay? So Cramers Rule, and again, he just noticed a way to actually solve a system a different way. And if you really start looking at the math that he did, which is kind of tedious, basically if you put an A and a B and a C and a D in there, instead of a 3 and a -4 and a 2 and a 5, if you put variables in there and then actually computed Cramers Rule, you see that all he did was come up with patterns for actually doing an elimination method. That's what he did, okay, or a substitution method. So watch what he's doing, but you can do it kind of brainlessly now without having to think, okay, what do I multiply the top by, or what do I multiply the bottom by, and then what do I do? It's just super simple, plug the numbers in and go. So for Cramers Rule, all you have to do is look at the original expression, make sure all the x's and y's are lined up underneath each other. So if this was like x and y, and the next one was like y and x, switch them so that the x's are over the x's, y over the y's, equal over the equals, constants over the constants. Okay? And then what you're going to do is create 3 little 2x2 determinants. And with those 3 determinants, you're going to be able to solve this system. All right, so the first one, they don't really have names, I'm just calling them this. The first one I call the D determinant because there's also a D sub x determinant and a D sub y determinant. Okay? So the first one I find, basically you're going to ignore the constants. And you're going to take the coefficients of these, which is like what we call the coefficient determinant. The 3, the -4, the 2, and the 5, and you're just going to put them in a determinant and evaluate it. And you get 23. And 23 in and of itself means absolutely nothing, but you're going to use it in a second. Okay? Now here's the part that makes it Cramers Rule. The next determinant, the next 2, the dx and the dy, and by the way, if there was a third variable, you have a dz, right? Or maybe a abc, depending on what variables were. The next determinant, I'm going to still use the 3, -4, 2, 5. But this time, wherever the x's were, which was the first column, I'm going to replace those with the constants. So everything's going to remain the same except, so the -4, 5 don't change, but I'm going to replace where the x's were in this equation, and since x's came first, I'm going to replace them with 11, -8. And I'm going to evaluate that determinant, 55 minus the 32, 23. And that's just a coincidence that those are the same. Okay, they're probably not going to be the same all the time. I just made a problem up with nice, simple answers. Now, for the dy determinant, what do you think you do? So, wherever the y's were, wherever the y coefficients were, which is the second column, I'm going to replace those with the constants. And just leave the x's from the original problem the same. And then I'm going to evaluate that. -24 minus 22 is -46. And when I'm done, I'm going to take those 3 determinants, and I'm going to determine what x and y is, or are, from those 3 values. And the x will always be the, sorry, where is this? So, down here. The x will always be the dx that you just found over the d, and the y will always be the dy that you just found over the d. So the d determinant, the one that came from just the coefficients, is always the one that's in the denominator. Okay? And the dx and the dy are the ones that are in the numerator. And then you just do the division and you get your x and y. Now you look at this whole page and you're like, man, that's a lot of work, but it's really not that bad because a lot of times you can just scribble these down, 1, 2, 3, eyeball the answers, boom, you're here. Otherwise, you're doing the elimination method or the substitution method or whatever. Y'all with me? Now, on a 2x2, most people would go, man, why are you doing this? It's so much easier to just solve it with elimination or solve it with substitution. And that's fine. It may be. On a test, just do what I ask, and in the future, solve whatever way you want. Okay? But look how this is kind of nice when you get to a 3-variable system. Now, a 3-variable system, I don't even know if we've done one this year, but 3-variable systems can be a little trickier to solve. Okay? Because 3-variable systems usually require, if you do elimination, you got to like put these two together and get rid of your x's. And then maybe you put these two together and get rid of your x's. And that would give you 2 equations with 2 variables. Then you got to get rid of maybe y's with those. And it ends up being this multi-step process with lots of room for careless error. Or you can do Cramers Rule. And what does Cramers Rule say again? How do you find the D determinant?
It's just the x, y, and z variables.
The x, y, and z coefficients. It's the coefficient matrix. Now again, make sure the x's and the y's and the z's are lined up. So take the x's, the y's, and the z's, boom, 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 evaluate the determinant. I chose the diagonal method on this way because it's an old worksheet. If it were me now, I'd probably be using the expansion by minus. And I get my D. All right, then I go, how do I find the dx, dy, and in this case, dz determinant?
Replace the x coefficients
With the
answers.
with the constants, right? So you see that 14, 20, and 1? I'm replacing the x column with 14, 20, and 1. If I'm finding dx. I'm replacing the y column, 14, 20, and 1, to find dy. And I'm replacing the z column, 14, 20, and 1, to find the dz. Now, the downside of all this is you do have to do 4 3x3 determinants. But hopefully by now, and I'm not going to give you brutal numbers, and I usually give you a nice little gift, and that is your answers usually end up being pretty clean. They're either pretty simple fractions like 1/3 or 1/2, or you get nice neat numbers like you can see here. That goes into that 4 times nice and neatly. That goes into that twice. Are y'all with me? So that's x, y, and z. Now, can anybody anticipate a problem with doing Cramers Rule? Can anybody anticipate solving and getting to a point where you go and you plug stuff back in to find your x, y, and z, and something bad happens? If they cancel that completely, you'd still have 1. What would be? Zeros in the bottom. So what would happen if you go to do this and you solve for your D determinant and it spits out a 0? What do you think that meant? If you plug a 0 in the denominator, it's clearly undefined. Okay, it can mean one of 2 things. It can either mean there's no solution, or actually it can mean you have infinitely many solutions. But Cramer can't answer it with this rule. Now, you're going to have no solution if you want to write this down. I have this somewhere in the notes. Okay? If you can, and I'm reminding you about this. This is a basic equation, right? A couple lines. What happens when you have no solution on a couple of lines? What does that mean? They're what?
Parallel.
Parallel? And parallel means they have same slopes. And look at this. The slope of that and the slope of that, if you do negative a over b, same thing, right? Or if you solve for y, you can see the slopes are the same. But clearly these aren't the same lines. Because if I multiply that by a -2, I don't get 3, do I? Are y'all with me on this? So these had the same slopes, but they weren't the same lines. And if I try to solve this with Cramer's Rule, look what happens. I did the Cramer's Rule stuff right below. Cramer's Rule, I get a 0 for the D. That was the indicator we were just talking about. If I'm going to be dividing by a 0, it's undefined. But look at the numbers on the top. I actually got answers on the top for the dx and the dy. So if you ever get 0 in the denominator, it means that there's not one answer, but it might mean none, it might mean infinitely many. In this case, none. There were no solutions to this, because these 2 lines were parallel. Are y'all with me? But look at this line. What if I gave you these 2 lines? Now these are the exact same line. Look, if I multiply through by -2, I get -4x, positive 5y, -14. What do the same lines look like? They still have positive slopes. I mean, the same slopes, but what? What else? Everything's the same. Same y-intercept, same points, same everything. And guys, look what happened when you tried to solve this before. Unlike the one above this, which had 0 equals 10 or something like that, this one's 0 equals 0. Well, look what happens when you do Cramers Rule on these. Not only do I still get 0 for the d, but I also get 0 for the dx and 0 for the dy. So if I ever get 0 for the d and the other numbers exist but are weird, that means a no solution. But if I ever get 0 for the d value, the determinant value, and for the other things, that means I'm going to have infinitely many solutions. And in this case, the actual line itself. Are y'all with me on this? Now that's with lines. What are 3 variable equations representing?
Oh, the z-axis.
If there's a z-axis, what are we talking about?
3 figures.
Do what? It's 3-dimensional, but what? A plane. Now let's stop and think for a second. Come back to this. Original problem we just did, not the original, but that one right there with the 3 variables. These are 3 planes. I'm asking you to solve. You did. And you found that when x is 2, y is -1, and z is 4, that in this plane, there was one point, in this system, there was one point where these 3 planes intersected. Now, you know a plane could be like this wall, right? And maybe this floor. And maybe that side wall. Where would that side wall and then this side wall and this floor intersect? Down the corner. That's what you just found. You found where they intersect. Now, what if they don't intersect in a point? Like, what if it's this side wall and this ceiling and this floor? Where do all 3 of them intersect? Nowhere. Ceiling, floor, and this, they don't all 3 intersect somewhere, right? That would be a null set. That would be a situation where your d value on the bottom was 0, but everything on the top was just weird numbers, like 4 or -7 or 12.
So that'd be like the one where you got 0 for d, and then like the other like 2 had numbers.
Different numbers, exactly. That would be no solution. But what happens if it's this plane, this wall, this floor, and then maybe another plane that's out here that's intersecting right there at the crease of that? That intersection ends up being a line, doesn't it? How many solutions is that? Infinitely many solutions, right? Kind of like pages in a book. Like if you take 3 pages and they might go in different directions, and technically they're not intersecting, right? They're not like fused together, they're maybe glued, but they're really actually separated. But they have the illusion of kind of being like this, right? But don't they all intersect at that seam? Now how do I write that answer? Well, that's probably for another day. But the point is, aren't there a zillion answers right there? What do you think that looks like when I do Cramers Rule?
A line.
Yes, but when I apply Cramers Rule, what do you think happens? It's all zeros everywhere. So when you see all zeros with 2 lines, it means it's the same line. But when you see all zeros with Cramers Rule, it doesn't mean it's the same plane. It just means the planes may have intersected at the same line. Could have meant the same plane, but that's usually pretty obvious, right? Because you can look up here and go, literally, the plane looks exactly the same. So let's just talk about this a little bit. I know people are kind of looking at me like I'm crazy right now. So let's just take a look. But here, if you look at these notes, I'll tell you, we'll just do a couple, and I think you'll be fine. So right here, solve using Cramers Rule. So what 3 things do I need to find?
The d,
And what is the d?
x and y coefficients in image.
So 3, -5, 4, 2, I'm completely ignoring the 1 and the 10, and I value that, and I get 6 plus 20, done with that. What's the dx? d sub x. What am I going to do here?
Replace the 3 and 4 coefficients
With?
the constants.
So I'm putting the 110 in there for the 3, 4, because that's where the x's were. And listen, if the x's were in the second column, and you didn't want to move them, that's fine. Just put the 110 in the second column. You just put them wherever the x's were. And then what else do I put in here? -5 and the 2, everything else that was in the original. So I get 2 minus the negative, so 2 plus 50. And how do I find the dy?
You replace the y coefficients with the constants.
So I put the 110 over there.
And you keep the x coefficients the same.
And I'm going to keep the 3, 4. And I get 30 minus 4 is 26. And from this, how do I find x and how do I find y? So I divide the dx by the d, and that gives me 52 over 26, which is 2. And to find the y, I put the dy over the d, which is going to give me 26 over 26, which is 1. And I normally make these where your answers are kind of nice, where you have some level of confidence that you get it right. So if you end up getting like 94 over 26 and you're like, that doesn't go in there nicely, or it doesn't give me a nice clean little fraction, or something, if it's something really weird, you probably made a careless error on your set. All right, now what about this one? I want you to see this. Now, if you didn't know anything about Cramers Rule, what happens if I multiply the top by a -2? Wouldn't I get negative 6x positive 4y equals negative 24?
Yes.
What do I know about negative 6x plus 4y, negative 6x plus 4y?
They're the same slope.
The same slopes, but are they the same lines?
No.
So if I have the same slopes but not the same lines, then would these ever intersect? So what do you think's going to happen when I do the Cramers Rule if these have no solution? The d is going to be 0, but what about the dx and the dy? They're going to be just other random numbers. Okay? So we can expect that. But if you don't even notice this, look, you're just cruising along. I call it teacher mode. Or like when I make a key out, sometimes I'm not even thinking about tricks or anything. I'm just trying to get through the key. Sometimes I get to the end, I'm like, man, that was so hard. And I go, oh, crud, there was a little thing I noticed. It would have made it a lot easier. But if you just plug along with here, and I said Cramers Rule, check out what happens initially. 3, negative 2, negative 6, 4, 12, minus 12, bam. So right there, I know that the slopes must have been the same. Either they're not the same line, or they are the same line, but I know something's up immediately. And then when I go to the dx, I replace the x column so that 12, 7 comes in here. Negative 2, 4. And I get 48 plus 14 is 62. If I've done my math right, and the dy,
3, negative 6, and 12.
that's right, bring down the 3, negative 6. And I get 21 plus 72, which is what, 93? Right? And right here, what's going to happen if I try to find x now?
62 over 0.
Yeah, I get 62 over 0, which is undefined. And what do I get when I try y?
93 over 0.
Which is undefined. But it's important that I may very well ask you, what does this tell you about these two lines? And if you just say there's no solution, that might be something. In this case, that would be right. There is no solution. But if I said, hey, talk about these graphs. Were they parallel, not intersecting? Were they parallel on top of each other? Were they intersecting? You should be able to tell me that they're what? Parallel, but not intersecting. Okay? And you know that because of this behavior, the fact that you got numbers on the top. And then number 3, let's check it out. Number 3, we got a big 3 by 3 here. What do you think you do when you're missing a term like that y?
0.
Just fill it in with the 0. Good. What do you think you do if it's not in order?
Make it in order.
Put it in order. I used to do that on a test. I would scramble up the X, Y, Z, and people would just miss it. And I was like, why am I doing that? So the book very well may do it to you. They may have X's on both sides, Y's on both sides. You got to make it look like this standard form kind of thing before you get started. So this one's going to take a little bit longer, so I might move a little more quickly through it. But how would I find the D? 1, 1, 1, 3, 0, negative 1, 1, negative 1, 2. Got to be honest with you, you can pick the middle row if you want because it's one less thing to do. But I honestly, if it's not a couple zeros in there, it's probably not that big of a deal to me. So I'm just going to do this. I'm going to expand by minors, but if you want to do the diagonal method, knock you out. I'm going to go 1 times its minor, which is 0 minus 1. And then I'm going to change the sign of that one. Remember, on expansion by minus, you change the sign of this? And then what's its minor? These four numbers? 6 plus 1, minus the negative is plus. And then I'm going to take that one, which I don't change the sign of, its minor are these four numbers, negative 3 minus nothing. So I like expansion by minus, it gets me there pretty quickly, and I get a negative 11. That's D. Now what's dx?
You gotta replace 131 with 520.
I'm going to put the 520 in the x's column, which is the first one. Copy everything else down. And I'm probably going to expand about this first row again. So you can do the diagonal method if you want, but I'm going to go 5 times its minor, and what is its minor? 0 minus a positive 1, so negative 1. And then minus 1 for the middle one, times its minor, 4 minus nothing. And then finally plus 1 times its minor, which is negative 2 minus nothing. And that gives me a negative 5, a negative 4, and a negative 2, which is also a negative 11. How nice. Now I've had people that do this before. Like I've given the question, solve this using Cramers Rule. And they go, okay, I'm going to use Cramers Rule to find x. Now that I have x, negative 11 over negative 11, that's not right.
Wait, no, you're right. Wait. Never mind.
So they literally followed directions, they used it, but then they just abandoned Cramers Rule because they got sick of doing 3x3 determinants, and they plug this back in here, and now they get y plus z is 4, negative z is, subtract the 3, negative 1, which means z is 1, and negative y plus 2z is negative 1. And from this they go, all right, now I have my x, now I have my z, that was really nice. And if I have x and z, I can plug a z in and get my y. Right? And you can go back and check. 1, 3, 1, that's 5. 1, 3, 1, that's 2. 1, 3, 1, that's 0. Huh, good. And I could say to you, but you didn't use Cramers Rule. You're like, yeah, I did. I used Cramers Rule to solve this problem. And I didn't have to do two more 3x3s. Right? So if you want to do that, but you know what I'm probably going to do on a test here, so you have to spend all day. I'm probably going to say, set up what you would do to solve for x, or set up what you would do to solve for z. And what would you do to solve for z here? Wouldn't you be doing this? So couldn't you just say, all right, set it up. Set up does not sound like evaluate. My dz would be the 5, 2, 0 right in there, right? Copy the rest of that down. 1, 1, 3, 0, 1, negative 1. There's my z value. And then my d is just 1, 1, 1, 3, 0, negative 1, 1, negative 1, 2. There we go. That's what I would do to solve for z. And it took me how long? 10, 15 seconds? As long as I knew what I was doing. So that's all I probably will do on the test, because I don't want you to sit there and do 5 million 3x3s to get everything done. I also might ask you a question like this. What if I said, hey, if d is 10, dx is 20, and dy is 5, what is x and what is y? Are you going to be able to do that? So you go, oh yeah, x is that over that, y is that over that, right? And then I would turn around and say this. Now what's x and y?
They're both.
Okay, and what does this mean about, what does this mean? What does this mean about the two lines in this system.
They're parallel and don't intersect.
So you'd say D&E, or undefined, undefined? And you said they were parallel but not intersecting? Y'all with me on that? And then what would this mean?
They're the same line.
They're the same line. Right? And that's probably where I would limit it in this class. It could get a little bit uglier. What if I said this about the two planes in this system? What if I gave you that and said solve for x, y, and z? You'd say what?
X,
1, 2, and 3. And what would you say now about the three planes in the system?
They're all undefined.
They do not intersect in one spot. They do not. Right? So you get D&E on all these because of the 0, but because you had numbers there, that means these three planes are like maybe the ceiling, the floor, and the wall. I mean, two planes are going to intersect somewhere unless they're parallel. 3, if they're not, they're going to intersect, but that doesn't mean they'll 3 intersect. Right? But what if you had that? What does that mean?
They're the same plane.
They might not be the same plane, but they intersect on a seam, like the 3 that intersected. So they might be the same plane, but all this tells you is they're all intersecting on a line. It'd be some weird three-dimensional line, which you don't know enough to be able to do three-dimensional lines yet. Because your lines are always defined with slope, right? You have a point and then you do rise, run. But rise, run is dependent on two axes, right? A y and an x. So if you throw the z in there, what do? Rise, run, scamper? I mean, you got to come up with something. So you have to totally change your definition to go to parametric equations or some version of a parametric equation, which we don't talk about till next year. And then hardly even next year. Y'all with me? Not too bad? Kind of fun? Math fun? Okay, so let's just take a look at, y'all mentioned some of these rules were bothering you. Did everybody do this worksheet? If you didn't, go back and look at it, but let's just run through it quickly. Have we done any of these in class?
We did the first 4, 2, maybe? On the video.
Oh yeah, maybe the first 4?
I think so.
Okay, so let's pick up at number 5. Number 5, you get a big 4x4. Do you really think I want you to do a 4x4 determinant?
No.
No. So there's got to be something going on. Now, if your answer to that is why wouldn't you want it? Remember, to expand, you can't do the diagonal method. To expand using a 4x4, what are you going to have to do? You're going to have 4 terms by 3x3s. You're going to have to do 4 3x3s. Why would I do that on a test sheet? Now, I might say set it up. Guys, by the way, if I say, hey, set up what you would do with expansion by minors, and I give you a column. Maybe I say third column. Then I need you to go, all right, 4 plus minus plus, 4 is in a plus spot, times its minor, and fill it in. And then change the sign of the negative 12 times its minor and fill it all in. You go with me? And then keep the sign of the negative 4 times its minor and fill it all in. And then you can ignore the 0. So if I tell you third column and just say set it up, don't evaluate, then you would set it all up. Now granted, don't do that when you're setting it up. You fill in the numbers, right? So you'd come in there and say, all right, the real minor of 4 would be 7, 8, 13, negative 2, 3, negative 5, 9, 2, 1. And you would fill these numbers in. But that's all I would do if there wasn't a trick. I just want to see that you would have known how. And I will do that a lot in this test. If you solve these or simplify these when I say set it up, you're not going to get finished with this test in 50 minutes. So if it says set up, man, just set it up, move on. And make sure you pick the right column that I tell you. I'll tell you which column if I give you one like this that I don't want you to solve. All right, what about this? We talked about that trick, right? So for those of you that were confused about some of these properties, the book really focuses in on Gaussian Jordan elimination, where you add the rows or columns together. That's their trick. And most of these tricks come from that. But on this one, we noticed expansion by minors would get us there. But what's the trick for a 4x4 that goes up to the right?
You just multiply that middle diagonal together.
So you multiply the diagonal. Is that it?
Yes.
I negate it.
Oh yeah, sorry, because of this.
Or don't I negate it? I don't negate it. Why?
Because it's an even number?
No.
Because it's going up around.
We said 2x2s and 3x3s,
Oh my god.
we negate the diagonal.
Oh, yeah.
But 4x4s and 5x5s, we what? We just multiply the diagonal. And this is a 4x4. So that's all I have to do. Now it ends up being negative because it ended up being negative, but I did not go and negate it. The negative was already there. But had this been a 5x5, I would have had to put an extra negative in there. I'm sorry, if it had been a 6x6, I would have had to put an extra negative. It had been a 3x3, an extra negative in there. Right?
Right.
Okay, what about number 7?
This one is going to be negative.
Okay, yeah, so coming down to the right, it's always the diagonal. You will never have to worry about adding or multiplying by a negative. Okay, so, but notice, I didn't do anything to that sign at all. And that's true for anything coming down like this. What about this one, number 8? It's a 7x7. So 6x6s and 7x7s, you negate them. And if you look carefully, you'll notice there's always going to be lots of 10s in there, or negative 10s. So there's a 10. I mean, you can write them all out if you want. All right, but you're going to negate that. So the 2 of the negatives become positive, but you still have 1 left, right? And then that times that's a 10. I already got a 10. That tacks a couple zeros on there. So all I really have left is that 2, that 7, and that 3, which is a 42. So 4,200, but negative. If I were you, I would definitely set it up and have this negative sitting out there so I can see it. You know? Have that negative out there so I can see it, even if you make a careless error multiplying it together. What about number 9? I'm going up to the right, so I definitely have to be concerned with size, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 by 8, 9 by 9, what?
Don't negate it.
Don't negate it. So on this thing, 2, negative 1, 5, 2, 7, negative 1, positive 1, 2. Do not negate it. So the 2 negatives that are already there become positive. This 5 and the 2 is a 10, and I'm left with 2 7s, 2 2s and a 7, so 280. What do you know about this rule on number 10?
It's going over and
So I'm adding 1 as I move to the right.
and you're adding 4 as you go.
I'm adding 4 as I go down. Is that consistent throughout the entire problem?
Yes, sir.
Is it important that it's consistent throughout the entire problem? Only 3 rows or 3 columns would have to have that condition. If 3 rows or 3 columns, so it doesn't matter whether this is 13, 14, 15, 16 or Happy Face Banana, Christmas Tree, Orange. Does not matter what it is on the bottom, because if you have 3 rows or 3 columns that match that condition, this is always going to be 0. So I'm feeling for this problem. Okay? Or you too may be dragged in infamy for the rest of my teaching years. How many years have I been telling that story? 19. 18. Although I doubt I have 18 years left here. What about number 11?
It's also 0.
Plus 3, plus 3, plus 3, all the way across. Oh wait, plus 3, plus 3, plus 2.
Doesn't matter.
Doesn't matter. What about going down? 2s, up, 1. But it doesn't matter because as long as 3 rows or 3 columns are met, which they are, you know it's going to be equal to 0.
Does it have to? Do they have to be like by each other for it to work? Or like in number 12?
Let's take a look.
Well, never mind. But
The short answer is no. Because let me show you, like, what if that was this is the only number off, right? What if that was a 14, but this was a 17? So you're like, crud, adding 3 right here, and this is adding 3, and this I'm adding 2, but then I jump to 4. But watch, remember the process of this? If I pull the negative out, and added these together, I get 2, 2, 2, 2, right? Y'all remember that?
Yes.
Like, again, if I factor a negative out of the top row, and then add these two together and replace the result with one of them, or replace one of them with the result, I would get 2, 2, 2, 2. So I could replace this with 2, 2, 2, 2. Now what about this? What if I took a negative out of this row? And then added these together, what do I get? 4, 4, 4, 4. This time, right? Y'all with me? What's that and that? 4, 4, 4, 4. Now, these don't match. That would be an extra negative, yeah. But couldn't I take a negative 2 out of this? And then they're opposites? And then what would happen if you added those two together? 0. And if you have a 0 on the whole row, what does that mean?
0.
Doesn't matter what's out here, it's going to be equal to 0, isn't it? So you just came up with another rule. So even if the pattern is interrupted in the middle, if there are 3 rows that look like they were on pace for a nice pattern, right? These 3 fit it. It's just that if that one number, like if this number is fine, let's say this number is off. If you had 3 rows that would have fit a nice clean pattern, and these 3 did, you with me? Even if they're not adjoining, you'd still be okay. Which is worth remembering. And that's the kind of thing that changes from year to year. You know, you go to a math term and they're like, all right, everybody knows that boring rule. Let me change one thing and I'll throw them off. Except usually they change things now that don't end up in 0, because most people go if in doubt 0 when they hit something like that, because they just assume. So now they're starting to tweak them where they're not 0. What about this thing?
Also 0.
Also 0. This thing.
Couldn't say.
2, 2, 2, 2, 2, 2, 2, 2. 1, 1, 1, 1, 1, 1, 1, 1. Now, what would happen if I join these two together?
1.
I'm sorry. What if I factor out a negative 1 and join all those two together?
1, 1.
I get all 1s. What if I factor a negative out of this row and join those together?
1s.
More 1s. What happens when you have any 2 rows or any 2 columns that are the same?
It's 0.
0 times anything? But again, you see less and less of these at tournaments because more and more people go, man, if I don't know how to do it, I'm just putting 0. And now you got people that don't know how to do it getting it right. And the goal is to see if people that do know how to do it are going to get it right. So if I saw a 5x5 or a 6x6 and it didn't have a diagonal thing going on, I would probably assume it's 0 unless it is something, and I don't know if I put one on here, but I can show you one in a second. We got 6 minutes. It's something like 15. Now what do you see going on in 15?
A lot of 0s.
A lot of 0s, and I got a diagonal that looks kind of nice, but then there's that. So here's what we're going to do. Rather than grab our ankles, assume the position, and take our beating, what are we going to try? We're going to try something like a rat in a maze, right? We're going to sniff around a little bit. There is something I can do. Now, I do not want to do a 5x5. A 5x5 means I'm doing 5 4x4s. And each 4x4 would mean 4 3x3s. I do not want to do 20 3x3s. But I'm also of the understanding that math tournaments don't want me to do 20 3x3s either. They want to see what I know. So I'm just going to try something. Like a rat in a maze. Just sniff around and see. So I can do expansion by minors, can I? Right? Well, what row or column would you pick if you were going to expand by minors? Pick one.
The first column.
This column? Okay, so let me write it. I'm going to have to do 2 minor cofactor combinations, right? Let's hope for the best. 2 times its 4x4 minor, which is, now check it out. The minor of 2. Wouldn't that be this?
Yes.
Whoa, what do I see right there?
Oh, it's a diagonal. Yeah.
It's a diagonal. So what is all this? I don't even have to write it out. It's just 2 times its diagonal. And if it's going down to the right, it's always just the diagonal, right? 5 times 7 times negative 1 times 3. Done with that one. And then 10, no, you said column. 3 would be in the plus, minus, plus, minus, plus spot. So don't change the 3. Let's look at 3's minor. Not as good, so I'm going to write that down. But it's still not bad, check it out. At first glance, you're like, oh man, it's killing me. But nope. Now, without bailing on the problem yet, what would you do to evaluate that minor if I gave it to you? Which row or column would you pick?
First row.
The first row, okay. So if I pick the first row here, this would be a plus minus plus a negative 10 times its minor, wouldn't it?
Yes.
So wouldn't I have this? Wouldn't I have that 3 times that negative 10 times the minor of negative 10? Now what would the minor of negative 10 be? It'd be that, right?
Yes.
Oh, a diagonal.
Crazy.
5, 7, negative 1. So all I got to do is that, and then come in here and take this 10 and that negative 21, and then whatever I get from this, add them together. Are y'all tracking with me on that? Now, if I just look at it initially, it's intimidating. And that's what they want it to be. They want it to be like, man, I'm not doing 23 by 3 determinants. That's ridiculous. And you quit and you move on. That is assuming the position. Doesn't end well for you. Okay? But if you just try something, most of the time it's pretty good. I used to teach a formula on this. I haven't seen it in probably 20 years, so I quit teaching it, so you can ignore that. There is a little trick for these, but that would just stink, so don't bother with that one. Y'all with me? All right, that's all I got. We're reviewing tomorrow. A little quick Q&A review on Wednesday. Bring me your questions. Email them to me, something. If you have any at this point, let me know, and I'll try to get you straightened out. If not, again, Q&A, we can do some problems on Wednesday at the last minute if we need to.
Test Thursday.
Test Thursday or Friday if you're at home.